know what you mean by I am. I found this on the web.
Okay. Good morning. So today we'll be seeing what is discrete cosine transform. We know different kinds of transforms like Fourier transform, Fourier series, discrete time Fourier transform, discrete Fourier transform, etc. All these maps our signal into frequency domain depending on the signal characteristics, whether it is periodic or discrete or however it is, you have an appropriate transform to the frequency domain. Um, so this is DCT. What we'll be seeing today is DCT, which is called discrete cosine transform. What discrete cosine transform do is it does a transformation in terms of
I didn't get that. Could you try again?
so the discrete cosine transform is the equation is sigma. So I varies from 0 to n minus 1
I'm sorry.
cos 2i plus 1
I thought so.
by n.
I didn't catch that. Could you try again?
Okay, let me
What can I do for you?
1 minute. Okay, coming back. So what discrete cosine transform basically do is, um, you know that in Fourier series, what does Fourier series or Fourier transform do? Let us take the case of Fourier series. In Fourier series, you have a summation of signal or f of t, a periodic signal is represented as sigma. Say you may have a0 plus n equal to 1 to infinity an cos omega nt plus sigma n equal to 1 to infinity, or say k equal to 1 to infinity bk cos omega nt. Okay, and what is an? An, how do you find an? An is integral, say minus to infinity you are basically finding, or you can find it in one period, 0 to t, f of t cos omega n t. So the an or the coefficients, these are the coefficients of the Fourier series expansion, and you find these coefficients as correlation of ft with cos omega n t, where n varies. If you want to find a1, this become cos omega t. So basically you are correlating your signal f of t with cos omega t. If you find a2, you are correlating your signal f of t with cos 2 omega t, like that. Okay, so this is the way you do Fourier series to find the coefficients a0 to whatever those values are. Similarly, you can find bn where you or bk where you correlate your signal f of t with sine omega n t dt, and you get a set of b1, b2, etc., um, which are the correlation to cos omega t, sorry, sine omega t, sine 2 omega t, sine 3 omega t, etc., which are increasing frequencies or multiples of frequencies, sine omega t, frequency of sine omega t, and sine 2 omega t, sine 3 omega t, etc. They are multiples. If this is f1, you have 2f1, 2f2, like that, 3f1. So these are multiples of this frequency. Now, this you can again find, instead of doing this in discrete cosine transform, where the transformation is not to the frequency domain, there is some transformation happening. So if you see the transformation here, you can see that it is sigma xi, I varies from 0 to n minus 1, sigma xi cos 2i plus 1 pi k by, it's not n, it's 2n, 2n. Now, what is this n, capital N? Capital N is the size of your signal, x of n under consideration. It may be a frame. If it is a frame of length n, that's also fine. So basically, n sequences, you are finding the corresponding discrete cosine transform. So normally n will be, say, 2 raised to something, 2 raised to, say, capital K or something, and it will be, say, 1024 frame size of 1024, where capital K is 10, like that. So this will be normally 2 raised to something. So this 2n will always be a 2n, and n itself will be a multiple of 2, and hence you have a 2i plus 1 here, which is an odd value which will not be multiplied or which will not be divisible by 2, capital 2n. So that's why this 2i plus 1 term came. Now, if you analyze this particular term, sigma xi cos 2i plus 1 by k by capital 2n, which is represented as capital xk. So to to not to confuse with discrete Fourier transform, I will put a small c here, notating that this is cosine transform. So xck is basically sigma xi cos 2i plus 1 by k by 2n. Okay, so if you take I equal to 0 to n minus 1. So what basically happened in say Fourier series Fourier series where this can be considered as a coefficient is you have discrete terms here instead of f of t is continuous here. Similar to that, you have xi here, but the difference that you can notice here is if you in this integral 0 to t ft cos omega and t dt, you are basically finding correlation of ft with cos omega and t, where n is constant, n may be 1. If it is fixed to 1, this becomes cos omega t. So you're finding the correlation of the signal ft with a particular frequency cos omega t. But in this case, you can see that I varies here. So if you give a particular value for k, say k equal to 4 or k equal to 1 itself, then you can see that cos 2i plus 1 pi into 1 by 2n is basically, in this case, I varies. If I varies, the cosine terms cos 2i plus 1 pi k by n by 2n also varies. The frequency also varies. So it's not just a correlation of xi with a cosine term, but the cosine term also have a varying frequency. So why do you go for this kind of transformation? The most attracting feature of discrete cosine transform is that you can easily find the inverse discrete cosine transform using a similar, almost similar equation, and so that coder and decoder, you know what codec is, right? It is the hardware which contain both coding and decoding machinery. So if encoder and decoder have almost same hardware, your chip for the codec or your codec chip will become very small because your hardware for encoding and decoding is similar. So DCT is an example for that, where encoding and decoding can be done with very similar hardware. So we shall see how it is and what is being done there. Okay, so xc, I'll write it again, xck, which is the discrete cosine transform, can be written as sigma I equal to 0 to n minus 1 xi cos 2i plus 1. This is for making it odd, by k by 2n. And for I equal to 0, what happened here for I equal to 0? This become cos pi k by 2n. Right? Cos pi k by 2n is cos k, or it's a multiple of cos pi by k. This become 1. And for I equal to 0, you will put a 1 by root 2 here, and a normalization factor of root 2 by n will also be here. So you'll have a ci term here. You see, not ci term, ck term, which can be taken outside. So ck is basically, it is 1 by root 2 if k is 0. If k is 0, what happened to this? This become cos 0 and this become 1, and you have root 2 by n. To cancel out root 2, ck will help in cancelling out root 2, and when you normalize this, you get, since the summation is from I equal to 0 to n minus 1, there will be one term, each of them will be cos 0 is 1. So you get a normalization and root 2 cancels. And ck is 0 else. Okay, not equal to 0. K equal to 0, it is 1 by root 2. Otherwise, it is 0 for k not equal to 0. So this ck is also included here. So the actual equation is root 2 by n Ck sigma I equal to 0 to n minus 1 xi cos 2i plus 1 pi k by 2n. Okay. So this is xck, which is the discrete cosine transform coefficients. Now to find inverse discrete cosine transform, what you do is you can use the same algorithm. Ck will go inside, so it will be sigma ck xck. Xck is the coefficients you have for the discrete cosine transform that you are using for finding the xn. So k varies from 0 to n minus 1. You have n minus 1 values. Cos 2i plus 1 by k by 2n. Again, root 2 by n. Ck is inside. So this gives x of n. Or in this case, you have yeah. So the beauty is that you can use the same coding hardware for decoding also, because you are just multiplying everything with cos 2i plus 1 pi k by 2n. Now let us see this, what happens when you do this for a two-dimensional thing. And what do you mean by two-dimensional signal? Any image can be considered as a two-dimensional signal. Take this signal. You know that each pixel is represented as so consider each of these array as one pixel. This is one pixel. You can do discrete cosine transform for this using a double summation where sigma, say let us take L and M. So L equal to 0 to n minus 1. If this is of size say M and this is of size N, sometimes they may be equal. Then you have two summations, different summation, n equal to 0 to m minus 1. Inside you have x, if the signal is xlm, any general point can be taken as xlm. So you can find using xlm, you take the summation, you will have two summations, cos 2l plus 1 by 2n, you have pi k multiplied by xlm, yeah, xlm is already here, cos 2m cos 2m plus 1 by 2n into pi k. So if you do this and you have CL and CM, where they become 1 by root 2 for L equal to 0 and M equal to 0 respectively. So by this way you can find the discrete cosine transform for two dimension, where xc can be say u and v. You can find an corresponding inverse for inverse discrete cosine transform also. So each pixel is this is x00. So you can substitute what the value of x00 is. This may have some value, say from 0 to 255 or something, depending on how many bits you have used. Um, if you use 8 bits, you will have 0 to 255 different values, and this could be therefore different colors like red, green, and blue, and there could be three different arrays or three different values for this particular pixel. So with those substitution, you can find what is the coefficient corresponding to XCV. And the beauty here is that when you if you see that XUV, some of the values of XUV are very small, you can neglect that. XUV is very small, then you can neglect that, or you can put a threshold such that those values below the threshold you can neglect. So what happens is that basically you get some compression. Basically you get some compression, or this is the mechanism that is used in JPEG compression for image. JPEG, the full form is Joint Picture Expert Group, where this is a standard for compression, and in normal JPEG they use discrete cosine transform for compression. So how does the compression happens? This XCUV, which is the discrete cosine transform coefficients, they are thresholded and very small values are neglected, such that you need not store those small values and your memory basically becomes smaller, and 1 MB picture may become say 500 KB or something, or even lesser, um, and you get a really compressed version of your original image. You would have heard about JPEG 2000 also. So JPEG 2000 is something similar to discrete cosine transform, but there instead of cosine waves, you use some small waves called wavelets. These are small waves which are called, like small drops are called droplets. You have small waves of finite energy, and in that case you are using wavelets instead of cosine waves, and there are different kinds of wavelets also. um, so this kind of wavelets, if you use wavelets, you call it wavelet transform. Wavelet transform that is used for JPEG 2000. So similar to discrete cosine transform, you have discrete wavelet transform also. Discrete wavelet transform also. And sometimes for some purpose you can generate your own wavelets for some applications. Actually, in my PhD work, I have found some wavelets for musical instrument processing. That wavelet is called SSM wavelet. Basically, this is Sinitish and my guides name Shikha and Murthy. These two are my guides. So this kind of wavelets give better compression, and that's how JPEG, from JPEG it came to JPEG 2000, which is even better, where you use wavelet transform. So in normal JPEG you use discrete cosine transform. So this is the way cosine transformation is done. So remember, discrete cosine transform is not taking your signal to direct frequency domain, because you are not correlating your signal directly with a single frequency. The frequency also keeps on changing, but the convenience is that you can use the same hardware with a small change for decoding, encoding, and decoding. Okay, so that's what discrete cosine transform is. I think with this we can stop today's session. Yeah, I hope you understood this. If you have any doubt, you can ask. And this topic will not be there for the first series examination, which we have been scheduled in on Thursday. I'll stop recording now.